Getting tomorrow's technology ready for the future is the purpose of the Technology Demonstration Missions Program. Taking today's most promising exploration technology and raising it to the level of maturity that mission planners require means that TDM puts the technology to the test. The projects include communication, materials, propulsion, and robotics. Key to any exploration program is effective communication. Current technology is hitting a bandwidth and wavelength ceiling. Tomorrow's missions will need a new technology. NASA is leading the effort to make laser light reinforce the current radio or RF-based communications. The Laser Communications Relay Demonstration, or LaserCom project, will provide an orbital test bed for a wide variety of scenarios to simulate future missions. In the near future, laser communications could increase the amount of information to tens of gigabits per second. This would be an improvement of data rates of between 10 to 100 times. The project will use laser light transmitted to a satellite payload and back to an Earth station to simulate and test a large number of possible mission scenarios. Another foundational technology being improved by the TDM program involves a basic component of all exploration missions: time. The Deep Space Atomic Clock project promises to reduce cost, improve space navigation, data quality, and the next GPS system. To test this concept, the project will fly the Deep Space Atomic Clock along with a GPS receiver on a commercial communication satellite. Ground-based systems require two-way communication. With an onboard atomic clock, DSAC allows for one-way navigation using NASA's Deep Space Network more efficiently. Eventually, this will enable deep space autonomous navigation. Communications and science payloads need advanced warning of solar flares. One way to do that includes station-keeping capabilities like the current NOAA Solar Activity Warning Instrument. The TDM Solar Sail project takes a previously tested propulsion technology and infuses it into an even better warning system 2 times closer to the Sun. The Solar Sail project pushes the technology to a practical application while simultaneously maturing the system so that future mission planners can choose it for a whole range of missions. All of NASA's technology demonstration missions are infusing mature technology from the realm of tested to ready and proven. But one of those demonstrations tests the very materials used for spacecraft construction. That project is a continuation of a heritage project called MISSI, Materials International Space Station Experiment. Building on the previous missions, MISSI-X seeks to provide low-cost access to space technology experiments using robotically installed plug-and-play features. MISSI-X plans to monitor the payloads by collecting data and photographic images in near real time. This allows for faster testing of materials and greater opportunities for educators to have easy access to the ISS as an experimental platform. Maturing materials and technology continues to be an objective of the TDM program. Sometimes that means putting instruments on the spacecraft of other NASA missions to further our collective knowledge. One project that does that is MEDLI. MEDLI stands for Mars Science Laboratory Entry, Descent, and Landing Instrumentation. MEDLI is an instrumentation suite embedded in and behind the heat shield of the Mars Science Laboratory, now on its way to a Martian landing this summer. The instruments gather real-time data on the atmosphere, thermal protection system, or heat shield, and aerodynamics during entry and descent. The MEDLI data will improve modeling and predictive capabilities for future missions, ensuring safer and less expensive missions to a larger variety of destinations. Along with the MEDLI data, NASA will see the fruits of research into entry in low-density atmospheres, like Mars, with the Low Density Supersonic Decelerator, or LDSD project. On Mars, for example, increasingly massive payloads and eventually human missions will require new ways to slow down to subsonic speeds high in the thin Martian atmosphere, allowing more landing site options. These heavier spacecraft will need large drag-generating devices, and the LDSD project will test 3 of them. 2 of the test articles will be inflatable inner tube type devices that surround the entry capsule. These 6 and 9 meter devices will be flown at supersonic speeds high in the Earth's atmosphere. The 3rd device will be a large 30-meter parachute tested several times to collect data for future exploration missions. All the previous exploration-enabling technologies will be dependent on propulsion to get to their destination. Long-duration missions require special considerations for the cryogenic propellant likely to be used for human exploration missions. On short missions, the natural boiling off of cryogenic fluids is not as serious a concern, but on long missions it becomes critically important. Propellants are heavy and expensive to lift to orbit and therefore too precious to lose. Anything we can learn to minimize this pays back huge dividends. There are a variety of approaches to meet this challenge, including passive systems like insulation and active ones like refrigeration. Another important part of this research is lossless transfer of cryogenic fluids and accurate measurement. Once completed, the flight demonstration technology projects will be extremely valuable, enabling us to reach our exploration goals beyond Earth orbit. As we begin to land even more ambitious crewed and robotic missions, one of the most challenging aspects of those missions will be landing in a large variety of conditions. The Autonomous Landing and Hazard Avoidance Technology, ALHAT, uses sensors to rapidly map the ground in 3D and measure range and velocity far more accurately than existing radar systems. ALHAT has already made tremendous strides in meeting the challenge of safely landing in some very difficult terrain. In the near future, ALHAT will be integrated with a vertical test bed named Morpheus to test and demonstrate advanced propulsion and safe landing techniques, critical for future missions. Some of those future missions will include humans, others robots, and some will be a symbiotic combination of both. The Telerobotics project is working on board the International Space Station, integrating robotics seamlessly into the nation's space exploration goals. From measuring environmental conditions on the ISS with free-flying robots called Smart Spheres, to dexterous two-armed humanoid robots like Robonaut 2, NASA sees a growing role for intelligent robotic devices. Telerobots can also save precious resources by doing extravehicular activities, working before and after humans. Each of these programs has been carefully chosen because they contribute critical technology and functional knowledge to our nation's exploration objectives. They improve safety and reduce cost. The Technology Demonstration Missions Program provides new knowledge and capabilities needed to enable NASA's future missions.